Okay, so we are in week 6, and this week it's mostly introductory linear algebra, covering concepts such as vector spaces, subspaces, basis, rank of a matrix, linear transformation, etc. So that's what we're going to look at. Okay. Right. So the first question uh, is about finding which of the sets is an independent set. So we first make a few observations. So the first observation is that if V is a vector space, and if V is finite dimensional, then the dimension of V is essentially the the maximum number of is the maximum cardinality of an independent set. So a set which has more elements than the dimension of V is necessarily not going to be independent. Okay. So let us first take an example uh, with with the second uh, with the second option. So here the vector space V is R4, and we are given four vectors V1, V2, V3, and V4, namely the vectors in this question. Now, what does it mean to say that what does it mean to say that um, a particular uh, set of vectors is um, is independent or is not independent? So if it is not independent, then that means that there exists constants alpha 1, alpha 2, alpha 3, and alpha 4, not all of which are equal to 0, such that alpha alpha 1 v1 up to alpha 4 v4 is equal to 0. These constants are not all 0. Now how do you check whether these constants exist or not? So essentially it is equivalent to checking. So there are a couple of equivalent ways to actually doing this. So the first is that so it so what uh, so it follows that for the set V1, V2 up to V4 to be to not be independent, So that implies the existence of these constants. So that basically implies this condition one, which I wrote over here. And what does this imply? So it's not just implies, it's actually is equivalent. So this is equivalent to saying that if you have a matrix, so let's say I construct a matrix A whose columns are V1, V2, V3, and V4. So these are the columns of my matrix. So if there exists constants alpha 1, alpha 2, alpha 3, and alpha 4, which which turn out to be equal to 0, so then that means that I can, so essentially what that means is that I have one column which can be expressed as a combination of other columns, as a linear combination of other columns. And what this means is that the determinant of A is going to be equal to 0. Simply because, so like assume without loss or generality that you can write this V1 as equal to some A2 V2 plus A3 V3 plus A4 V4. So now if you, so determinant, we know that determinant of a matrix A is independent if you add two columns to it. So, so the determinant of A is equal to, if I add the columns V2, V3, and V4 multiplied by these scalars, I get, let's say V1 minus A2, V2 minus A3, V3 minus A4, V4. And then you have V2, V3, and V4. Right, but this is equal to 0, and so the determinant vanishes. Conversely, if the determinant vanishes, then that means that, let me just write it. So conversely, this determinant of A equal to 0 implies that A is, which means that the rank of A is less than 4. Which in turn implies that one of the columns can be written as a linear combination of the other columns. And so that implies that that set would not be, so that set would not be independent. So for this particular problem, it suffices to construct this matrix A, which is 4 minus 4, 8, 0, 2, 2, 4, 0, 6, and 6, 3, minus 3, 0. And then there are several equivalent ways to solve the problem. You can either compute the determinant of A, or you can also compute the rank of A. In order to compute the rank of A, now one thing that we know for the rank of a matrix, the property of the rank of a matrix, is that the row rank of a matrix, uh, the row rank of a matrix is equal to the column rank of a matrix. So it depends. So it does not matter whether you're looking at rows or whether you're looking at columns. Okay. So one way is something which we looked at in the last class, where you can convert this matrix into a row echelon form. So a row echelon form is a form in which right. So let me just write it over here. Convert A into a row echelon form. And then check if there are no zero rows. If there are no zero rows, then the set is independent. And if there are zero rows, then the set is not independent. So it's an if and only if condition. So the number of non-zero rows that remain after you've converted A into the row echelon form will be the rank of the matrix A. Okay, so this is one way in which the rank of the matrix can be. So just to remind you what this row echelon form is. So the row echelon form is so we say that a particular matrix is in the row echelon form if uh, like if you look at the rows of that particular matrix, then uh, then okay, so let us just write it down. Um, so we say that A is in row echelon form if the following conditions are actually satisfied. So say for row I, the first non-zero element occurs at index at some index. So let's call that index Ci. Then what this means is that for each row j greater than I, all the columns till column Ci must be equal to 0. For each row j greater than I, A of j comma k is equal to 0 for all k less than or equal to Ci. And of course, we have the second condition, which is that for a row J, where J is greater than I, the non-zero element, the first non-zero element of J occurs after the first non-zero element of I, which means that Cj is greater than Ci. Okay, so this is how we can check for the second option. Now, what about the third option? For the third option, the space is actually the space of polynomials of degree 3. The space of polynomials of degree 3, of degree at most 3. Notice that the space of polynomials of degree exactly equal to 3 is not a vector space. Okay. So, so these are polynomials of degree less than or equal to 3. And the dimension of P3 is equal to 4. But we are given 3 elements to check for. Now, because there are only 3 elements, which is less than the dimension of P3, it is still possible that the set may not be linearly independent. So we resort to the above technique where we can first choose a basis. So the standard basis would be uh, to choose 1t squared and t cube as the basis for P3. So then you have a vector representation of these polynomials. You can construct this matrix A, where A is basically equal to 1 minus 5 minus 2, 3. 1 minus 4 minus 3, 4. 2 minus 7 minus 7, 9. Right. So here we can either convert this again to a row echelon form, or instead we can manipulate the columns. Okay. So of course you can ask the question that why are we allowed to change a matrix into row echelon form or perform these column operations? And the reason is basically this. So when you add two columns or when you add two rows, it does not change the rank of the matrix, because one can show that the process of adding two columns or multiplying or adding two rows is equivalent to multiplying the matrix with an invertible matrix. Now, because multiplying a matrix with an invertible matrix does not change its rank, so that's why uh, it's like a rank. It's a process that preserves rank. So we are allowed to perform. So here, instead of changing the rows, which we can do, we can again convert it into row echelon form and count the number of non-zero rows. If the number of non-zero rows is 3, we can conclude that it is independent. Instead, we can also do the same with columns. So let us do that with columns, let's say. So the first operation is to essentially zero out the second and the third columns. Okay. So we want to make the element over here 0 and the element over here 0. So we're going to do these transformations. C3 is equal to C3 minus 2 times C1, and C2 is C2 minus C1. So that gives us 1 minus 5 minus 2, 3, 0, 1, minus 1, 1, then 0, 3, minus 3, 3. In the second part, we're going to perform C3 is equal to C3 minus 3 times C2. And so we get 1 minus 5 minus 2, 3, 0, 1 minus 1, 1, and 0, 0, 0, 0. So you have 1, 0 column. So essentially, in this process, what we are doing, let me just write it over here. What we're doing is that we are we are making sure we are ensuring that that the first non-zero element of each column occurs in a unique row. That's all we're doing here. And we also have doing exactly the same as in the row echelon form, which is that if so this is the first point, and the second is that if if the first non-zero entry of a column Ci occurs in row J, then for all the columns, for all k greater than I, uh, the rest of the elements are all equal to zero. That is a of j comma k is equal to zero. Like for instance, if you take this particular matrix, here the first non-zero entry occurs over here in 1. And what we want is that the rest for the, if you look at the row in which this non-zero element occurs, then for all the columns, it should be equal to 0, as it is over here. Similarly, for the second column, the first non-zero element occurs in the second row. And what this means is that for all the columns that come after the second column, in this case, the third column, the rest of the row should be zeroed out. So this is not an independent set. We are finally left to verify this option. Yes. What do you want me to repeat? Like, which part did you not understand?
Sir, the first part, where you wrote down that first non-zero element of that part.
Here. Oh, this part.
Yes, sir. Yes, sir.
Yeah. So the first part is basically like this. The so if you look at the columns over here, so if you look at, so I'll tell you what this matrix will kind of look like. Okay. So for each column, let's say you have a column over here, some column over here, and you're looking at basically where the first non-zero entry of that column occurs. Okay. So when I mean first non-zero entry, that means that you look at the column and then you look at the row in which the first element is non-zero. Okay. So let's say you have a column that looks like this. So that means in the third row, you have found the first non-zero element. Okay. So if you record this for each column, okay. So for each column, you record the row index where you encounter the first non-zero element. Okay. Then this should be unique for all non-zero columns. Okay. I should write over here for each non-zero column, not zero columns. For each non-zero column, this number should be unique. In other words, if I come to this column, some other column over here, and if I encounter uh, the first non-zero element over here, the first non-zero element should not occur anymore in this column. It should only occur in this particular column. Okay. But notice over here that um, that if you have a element over here which is non-zero, let's say this element over here might also be non-zero. Okay, it's not necessary that this element over here has to be equal to 0, because the first non-zero element of this column is different from the first non-zero index of this column. So this condition is satisfied. Like for instance here, if you look at this matrix, here the first non-zero element for this column is in row index 1. For this, it is in row index 2. But uh, but the rest of this is actually non-zero, which is fine. The second condition is that if you have a particular column, and if you compute the uh, if you look at the particular row in which this first non-zero element occurs, okay, then the for all the columns that follow that column, that particular row must be zeroed out. Okay. So what this means is that, let's say for this column, I see my first non-zero element in row 1. It means that for all, if I for all the columns, this row 1 should now be equal to 0. For all the columns that follow this column. Let's say over here, this is some column I, let's say. Here, let's say I see my row, I see this at uh, row 3, then that means that for all the columns after I, which is I plus 1, I plus 2, and so on, this row must be zeroed out. Okay, this row must be equal to 0. Again, let's say I see this at over here for this some of the column J, then again the rest of the elements must be 0 over here. So this is if your matrix is in this particular format, then it is a kind of an echelon form. Okay, and uh, and from here, all you have to do is basically count the number of non-zero columns and the number of zero columns. Okay, the number of non-zero columns will give you the rank of the matrix. The number of zero columns will give you the nullity of the matrix. Okay, so I hope this is clear.
Yes, sir. Yes, sir.
Okay, so now if you have a vector space which is not a finite dimensional vector space, like for here example, we have functions c from minus pi to pi. So these are not, this is not a finite dimensional vector space. So again, here you cannot apply a matrix method because you do not have a finite basis. So here you have to basically solve. You have to basically check that, can I find constants alpha 1, alpha 2, alpha 3 such that uh, the linear combination of it is equal to 0. So in this case, it is very easy to see, because all you need to do is you just need to you have this 4 sine squared x. If you multiply this with 1 by 4, and you add cos square x, and you have 2. If you multiply that with minus half, then you see that this is equal to 0. So indeed, you have found constants, which the linear combination of which is equal to 0. So this is not independent. This is not independent. Okay. So for this exercise, the correct answer is B. Now let's look at another problem. Okay. So here, uh, we have. Uh, so this problem is saying that what is the dimension of vector space of all symmetric matrices where the dimension of uh, of this is 100 cross 100, but there are three additional conditions uh, which are also used. So the first condition is that the first row is 0 and the 100th row is also 0 and the trace is also 0. So if you have to draw the matrix looks something like this. So this row, which is the 0th row, is all 0. The final row, which is the 100th row, is also 0. And the trace is also 0. So this is 0, this is 0. Okay, and the trace elements, which is the sum of the diagonal elements, is also 0. Okay, so if you have if you just look at the set of all symmetric matrices, then symmetric matrices means that Aij is equal to Aji. So the space of all matrices, all 100 cross 100 matrices will have a dimension of 100 cross 100. But the space of all symmetric matrices will have a lesser dimension. Okay. So what is the dimension going to be? If you just look at symmetric 100 cross 100 matrices, if you ignore these additional conditions, if you just look at symmetric 100 cross 100 matrices, then you are allowed to fill in only the upper diagonal, let's say. So once you decide the elements of the upper diagonal, the entire matrix is determined because the elements of the lower diagonal are just going to be reflections of the elements of the upper diagonal. So we can only fill in the elements of the upper diagonal. So what are the number of elements that are there in the upper diagonal? So the number of elements in the upper diagonal. So if this is an n cross n matrix, then the number of elements in the upper diagonal is equal to 1 plus 2 up to n, which is equal to n into n plus 1 by 2. Okay. Now they have given you three additional conditions. So three additional conditions. The first condition is that the first row is equal to 0. So if the first row is equal to 0, then you no longer have a choice of what elements you can fill in the first row. Okay. So what this means is that from this number, you have to subtract n because n elements over here are already determined. Okay. But we also are given another condition, which is this last row is also equal to 0. If the last row is equal to 0, what this means is that the last column is also equal to 0. So let me just write it down. A row 100 is equal to 0 implies that column 100 should also be equal to 0 because it's a symmetric matrix. So if you now look at the last column, in the last column, um, there is another n minus 1 elements. N is 100 over here. Let me just write it down. N is 100 over here. So in the last column, you have another n minus 1 elements which are already filled out. Those n minus 1 elements are already equal to 0. So you cannot fill out those elements. So you have to subtract another n minus 1 from this quantity. Okay. Now you are left with the trace elements. And now you're left with the diagonal elements. So the number of diagonal elements is basically equal to n. It's an n cross n matrix. But out of those diagonal elements, the 100 cross 100 element and the 1 comma 1 element are already known to be 0. They're given to be 0. So you are left with n minus 2 choices. So n minus 2 choices are left with you. So out of those n minus 2 choices, it is given that the trace is equal to 0, which means that what we can write is that sum over of ai, where I is from 2 to n minus 2, so this is equal to 0. Sorry, not n minus 2, but actually n minus 1. This is equal to 0. So what this means is that out of these n minus 2 elements, so out of these n minus 2 elements, you can independently choose n minus 3 elements, because one of the element, let's just say, well, you can pick any element. You can say, for example, that a2 comma 2 is equal to minus of sum of ai, where I is from 3 to n minus 1. Okay, this is what this condition implies. Okay, so you have n minus 3 choices. One of the choices is taken away from you. So we have to subtract 1 again from it. So the dimension would be equal to n into n plus 1 by 2 minus n minus n, which is equal to n into n plus 1 by 2 minus twice n. Okay, that's going to be your answer. Okay, so I hope this is clear. Let's look at this problem now. Which of the following is a subspace of vector space R4? So when they say the set of all vectors lying on a line through the origin in the direction of this particular vector 1, 2, 3, 4. So what they mean, so the line through the origin um, is basically um, is basically a vector subspace of R4. Yeah, but Holi is tomorrow, not today. Right. So the set of all vectors lying, and tomorrow it's not possible to have a class. So according to NPTEL, we cannot have a tutorial on Wednesdays and Thursdays. So Friday already we have another class. So today is the only option. Okay. So the set of all vectors lying on a line through the origin in the direction of this vector. So if we call this vector as if you take this vector as 1, 2, 3, 4, V. So then all vectors that lie on the line and in the direction of this vector is basically going to be given by t times v, where t is any real number. Okay. So clearly this is a subspace of R4. The next is we are looking at the set of all vectors which is spanned by two vectors. So the set of all vectors spanned by two vectors would be given by some t1 times v1 plus t2 times v2. Clearly this is also a subspace. Okay. So A and B are both correct. How about the final option? The final option is vectors x, y, z, w which satisfy xy is equal to 1. So how, in order to check if two vectors, if a set of vectors is forming a subspace, you need to check two things. First, that if you have two vectors, whether you can sum them up, and the second is that if you have two vectors and if you multiply the vectors with any constant, then then that vector should also be in that set. So here, very simply, you can notice that so in any vector subspace, the zero element is always there. So here you can easily check that the zero element is uh, is not there, right? Because if zero was there, then this xy equal to 1 will not be satisfied. So it's not a subspace of R4. Okay. Uh, Before solving this, let's look at another problem first. Okay, or maybe we can just solve this first one. So find all x such that the rank of the matrix is less than 3. So this is a 3 cross 3 matrix. And if the rank of the matrix is less than 3, then that means basically you have independent rows or independent columns. Okay. But it but here in this case it is not clear exactly how you would convert this into a row echelon form or column echelon form. But uh, what we can do over here is we can just try to compute the determinant of this matrix. So we can compute the determinant of A and set this determinant of A to be equal to 0. So determinant of A is equal to um, 1 minus x squared minus x. And here you have x minus um, x minus x squared plus x times x squared minus x. This is set to 0. So you have 1 minus x squared uh, minus minus 2x squared plus 3x cubed is equal to 0. So you have to solve for x. Okay. Now let's look at this problem. Okay. We have okay. The dimension of the subspace x plus 2y minus z equals to 0 and 2x plus y plus w is equal to 0. Okay. Okay. So how do we actually solve a problem like this? So one way in which we can solve this is as follows. So first consider a map. So first consider a map from, so T is a linear map from R4 to R squared, R2. What this map does is it takes X, Y, Z, W and it sends it to X plus 2Y minus Z and 2X plus Y plus W. Okay. So what U is, so U is basically the null space of T. Okay. So the dimension of U is equal to the nullity of T. Okay. So now by the nullity plus rank theorem, what we know is that the nullity of T is basically equal to the dimension of R4. So it's the dimension of R4 minus the rank of T. Okay. So which is equal to 4 minus the rank of T. So what we need to do is compute the rank of T. Okay, how do you compute the rank of T? So to compute the rank of T, we first represent this, this linear map via a matrix. So the matrix is actually done very easily. How do you Okay. So how do you represent this in the form of a matrix? Well, so what you do is that you take the standard basis of R4. So R4, let uh, let E1, E2, E3, and E4 be the standard basis. So which basically means that your E1 is equal to 1, 0, 0, 0. Okay. Likewise, E2, E3, E4. Now, what is this T going to be? So this T is going to be a 2 cross 4 matrix. T is going to, sorry, T is going to be a 2 cross 4 matrix. So whenever you see something like a 2 cross 4, the way you should interpret it is that the if you think of this matrix, so we can always think of a matrix as representing a linear map uh, under some choice of basis. So here what this means is that, so when you write R2 cross 4, it means that it is mapping R4 to R2. Okay, so this is what the map is. And how do you fill up this matrix? So you fill up the matrix in this way. So you choose, let's say E1, E2, E3, and E4 is the standard basis of R4, and and let uh, let E1 prime and E2 prime be the standard basis of uh, of R2. So then what you do is that you compute TE1, TE2, TE3, and TE4. Okay. And you represent these uh, and you represent the vectors T1 up to T4 in terms of the basis elements E1 prime, E2 prime, and you form a matrix. So this is going to be the matrix corresponding to the linear map T with respect to the basis, with respect to the aforesaid basis. So let's compute it. So what is T of E1? So T of E1 is basically equal to, um, so X is equal to 1 and Y, Z, W are all equal to 0. So this is going to be equal to 1, 2. Okay. What is TE2? TE2 is going to be equal to, so here X is going to be 0, Z and W are 0, only Y is equal to 1. So this is going to be equal to 2, 1. Next, TE3. TE3 is going to be equal to minus 1, 0. And TE4 is going to be equal to 0, 0, 1. Okay. So, so the matrix of T corresponding to the basis that we have chosen. So that we have chosen two sets of bases. One is the E basis and the other is the E prime J basis. So corresponding to this basis, this matrix is going to be equal to 1, 2, 2, 1, minus 1, 0, 0, 1. Now what you need to do is you compute the rank of this matrix. Um, Now the rank of this matrix is, you can clearly see that the rank of this matrix is equal to 2. Okay. You can compute either row rank or column rank. It's going to be the same. So it's very easy to see that the two rows of this matrix are independent of each other. Okay. Um, so yeah. So the rank of this matrix is equal to 2. And so it follows that the nullity, the dimension of U is equal to 2 because the rank of T is equal to 2. So 2 is the right answer. So I hope this was clear. Um, okay. Now the dimension of the subspace W, where P is a polynomial, such that the integral of this polynomial is uh, is equal to 0. Where you're looking at P4. Okay. So so you're looking at a map from P4. So let me just write it over here. You have defined a map. Let's call this map um, let's call this map T. So T is a map from P4 to R. And what it does is that it takes a polynomial it takes a polynomial, something like P of X, not P of X, it takes a polynomial P in P4 of R and sends it to this real number, -1 to 1, pt dt. Okay. And we have to compute the uh, the dimension of the null space of P. Okay. So let us actually do it. It's not very difficult. So let's say T, we represent this polynomial as equal to P4, T bar 4, P3, P3, all the way up to P0. Okay. Then integral -1 to 1 pt dt is equal to integral -1 to 1 sum over of pi t power I, where I is from 0 to 4 dt. So if you carry out the integral, this is equal to sum over of I pi t power I plus 1 by I plus 1. It's from -1 to 1. So this is going to be equal to sum over I pi 1 minus 1 to the power I plus 1 divided by I plus 1. So essentially, what happens is that uh, only the only the even i's remain. The odd i's all get cancelled out. So we are setting this to be equal to 0. And what we get over here is uh, is this, that sum over of pi. So when I is odd, since I plus 1 is even, and that term is already 0. When I is even, what you get uh, is 2 by I plus 1. So you get 2 pi by I plus 1 is equal to 0 for I. Yeah, I mean, essentially, I over here is I over here is basically 0 to. So you get sum over of pi by I plus 1, I belonging to 0 to 4 to be equal to 0. Okay. Now, now there are various. Okay. So here we can compute this. This is easy to do. This is not difficult. Um, So what you will get over here is that the rank of this linear map is actually equal to 1. Okay. And because the rank of this linear map is equal to 1, the nullity will come out to be equal to 4. Okay. But here, none of the options is there, so null is the correct answer. But you will get that the dimension of this W will come out to be equal to 4. Okay. So I hope this was clear. Yeah, I mean, you will not see necessarily always problems which include like real numbers and matrices and so on. You can get one reason why we do linear algebra in an abstract sense is because it allows us to deal with many mathematical objects which which behave linearly, uh, in a sense that they form a vector space under addition and scalar multiplication. So functions being an example. So in this case, you looked at polynomials. So the reason why polynomials form finite dimensional vector spaces. If you fix the maximum degree of the polynomial, whereas general functions do not form finite dimensional vector spaces. Uh, but they are vector spaces nevertheless. Okay. So let T be a linear transformation, which is determined in this case. So, okay. So this is an interesting problem because um, the vector space on the left is polynomials of degree at most 4. And on the right, you have matrices, 2 cross 2 matrices. And it is defined in this way. Okay. So it says, what is the trace of the matrix? Okay. So whenever you have a linear map, okay. So here it basically says that what is the trace of the matrix of the linear transformations with respect to the two given ordered bases? Okay. So let me just state a fact over here. The trace of a linear map is independent of the choice of basis. Okay. So it does not matter what basis you pick, you will always get the same trace. So even though over here they have fixed the basis, they have said that you consider this to be the basis of P4 and this to be the basis of M2 cross 2, you will always see that the trace will come out to be the same. So nevertheless, let's still actually do this. So what is trace of T? So trace of T is defined as T11. Sorry, I mean, it's just the sum of the diagonal elements. So it's sum over of TII. Okay. Now, what is TII is the question. Okay. So when you have let me just briefly write what this is. We have seen this in one of the problems. So this is just a recap of that. So when you have two bases given, so let's say T is a map from two vector spaces U to V, okay? And let's say you have chosen a basis of U, let's say E1 to EM is a basis of U, and E1 prime to E prime N is a basis of V, then the matrix that you get with respect to the choice of these bases. So if you call this basis as B, and if you call this basis as B prime, then the matrix that you get T for the choice of B and B prime is given as follows. You you basically consider each of the elements of B. So you write TE1, TE2 up to TEM. Okay. Now you write each of these with respect to the basis E1 up to E1, En prime. So in other words, let's say TE1 is equal to, let's say it is equal to alpha, it is equal to alpha 1, um, alpha 1, 1, E1 prime up to some alpha N1 En prime. So if TE1 was of this particular form, then the first column would be alpha 1 1 up to alpha n 1. Okay. In general, if TEI is, or rather, let's say TEJ is of the form sum over of alpha ij e I prime, where I is from 1 to n. Okay. So then you will fill that particular column, let's say TEJ, you will fill that column alpha um, with alpha 1j up to alpha nj. Okay. So going by this logic, if you have to compute, so what we need to do over here to compute the trace of t, we need to compute this uh, sum over of TIIs. So for that, what you need to do is um, we need to evaluate this t. Let me just write it over here. Uh, Evaluate t on E1, E2, E3, and E4. Okay. For the second step is that represent this represent TE1 up to TE4 in terms of the basis vectors E1 prime up to E4 prime. So here I'm calling E1, E2, E3, E4 as these vectors, and these vectors I'm calling them as E1 prime up to E4 prime. So you represent these in terms of these vectors, and whatever the coordinate, let me just write it down. So the third is this TII is the coordinate of TEI with respect to EI prime. Okay, so that is TII. So let's do this for this example. Your basis elements are 1, x squared, x4, and x cubed, sorry. The first is you apply t on this 1. So t on this 1 is basically, well, it's basically equal to 0, 0, 0, and then f of 3. F of 3 is just equal to 1 because this is the constant polynomial. So for T1, if I ask you what is T11, so T11 is equal to 0. Okay. Why? Because you can write this term. So what is this T1? So T1 is basically equal to 0 times this particular matrix, which is 1, 0, 0, 0 plus 0 times, sorry, plus 1 times this matrix 0, 1, 0, 0 plus 0 times 0, 0, 1, 0 plus 0 times 0, 0, 0, 1. Okay. Now for the first element T1, you are supposed to look at the coordinate of this. So this is E1 prime, this is E2 prime, this is E3 prime, and this is E4 prime. So you're supposed to look at the coordinate of E1 prime. The coordinate of E1 prime is equal to 0, and so T11 is equal to 0, right? So next is T of x. So T of x is equal to, let me just copy this for convenience. Right. So Tx is equal to 0, 0. F dash of x is 1. And f of 3 is equal to 3. So your T of x over here, so if you write T22, so T22 over here is, so the coordinate is 3 um, with respect to this matrix. So T22 is equal to 3. So likewise, you can finish this computation. So Tx squared is equal to, um, so this is equal to 4. This is equal to 0. F of 3 is equal to 9. And f dash of 2 is equal to, uh, so f dash is equal to twice x. Twice x evaluated at 2 is 4. So you get this T33 to be equal to 0 again. Similarly, Tx cube, so this is going to be equal to 0, 0. Then f of 3 is going to be 3 cube, which is 27. And f dash 2 is going to be 3x squared evaluated at 2. So that's going to be equal to 12. Okay. So T44 is going to be equal to 12. Okay. I just want to mention one thing over here, which is when I stated this fact that the trace of T is independent of the choice of the basis, this is true. Let me just let me just qualify this thing. This is true when T is a map from the same vector space to the same vector space. So if T is a map from V to V, then if you choose a basis B over here, then the matrix with respect to B, the trace of this will always going to be independent of the choice of B. And the reason is as follows, because if you choose another basis, let's say B tilde is another basis, then the relation between the two matrices is going to be something of the form some P inverse T B. Okay. So when you take the trace of P inverse TB, P. Now trace of AB is equal to trace of BA. So you can interchange this and P inverse just becomes equal to 1. So you get the trace of T. Okay. So the trace over here is going to be independent of the choice of the basis. However, in this case, the linear map is not between vector spaces which are same. So the on the left, this vector space is um, is P4, and on the right, the vector space is M2 cross 2. So they're not the same vector space. So if so the choice of the basis here matters. Okay. uh, what we have done here is we have computed this with respect to the basis, with respect to this particular basis. Okay. But this is different from the basis given over here. Okay. In other words, we have basically reordered the basis. So if you reorder the basis, you will get a different answer. Okay. So here we'll get, so the basis that we have considered over here is 1 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. This is our basis, and the basis that they have given is is 1 1 and then 1 1. Okay. Now this is a permutation of the basis that we have considered, but the trace will not be independent in this case. So the trace will depend upon the choice of the basis. So if we choose this as the basis, okay, so then we get the trace to be equal to 15. Okay, but uh, but for a different choice of basis, you'll get a different answer. So I'll encourage you to finish the computation. So we have done the computation with respect to this basis. You have to finish the computation with respect to this particular basis, which is the basis which is asked in the question. And if you do so, you will find that the answer is equal to 21. Okay. So yeah, I hope this was clear. Uh, we are uh, we are at the end of today's session. So if you have any question, you can ask me. Um, Otherwise, we can meet the next week.